Good morning, dear students. uh, I hope you all are fine. We are resuming our discussion of the same topic that we left off before the Eid holidays. That was ultrasound. And I have the syllabus in front of me, and there are four subtopics in ultrasound. Let me quickly go over what we have finished so far and what remains in it, so we can start the new topic if we have time for today, because there is not much left in ultrasound. We started with the principles of generating ultrasound, and we had a comprehensive discussion on this topic. We understood that there is a piezoelectric effect behind it. We create a transducer for that purpose. We give it an alternating voltage that creates mechanical vibrations in it. And then we bring that transducer in contact with the human body of that part that is to be examined. Mechanical vibrations travel down the body, they get reflected, and that is the next part, and that is the principles of detection for detection of ultrasound for diagnostic purpose and all that detail that comes along with this. So one part deals with how we generate ultrasound, and the next part is how these ultrasounds are detected and they are made use of to create that image. So these are two different types of questions in the exam. I hope when you attempt past papers on your own, you will see these questions on your own, and I will share with you a few questions of that type. Because these are repeated, and I gave you the idea in last lectures, the kind of main points that you have to cover in the responses for these questions I discussed with you. But it's easy to see the answers as well, that the Cambridge suggests that these are the points that have to cover when we respond to a question like this. So this is the part where you just have to remember a few main ideas, and you just have to put them in order, because this is usually a 6 mark or 4 mark or 5 mark question where you have to cover the specific points. So this is already covered. The next part on which we did have discussion, that is about acoustic impedance. Acoustic impedance was defined and discussed as the product of density of a medium and the speed of sound. You remember I emphasized that this symbol is usually for speed of light, the small c, but in this particular topic, this is used for denoting the speed of sound in that medium. So speed of sound and the density of that medium, when multiplied, they give us a quantity which is known as the acoustic impedance of that medium. Acoustic impedance gives us an idea of how convenient it is or how difficult it is for sound wave to travel in a specific medium. And this is, of course, used for calculating the density of media as well. If I know the value of acoustic impedance of a medium, I know the speed of sound in it, I can easily calculate the density. So this is used for calculating density of various media. But more importantly, uh, we used this quantity to calculate uh, an important quantity that is known as reflection coefficient. Reflection coefficient is uh, simply the part of the incident radiation that gets reflected into the same medium, that gives us an idea how much of the incident radiation has gone into the next medium. That means how much is uh, transmitted into it. So more is transmitted means there will be a good image possible, and of course that gives an idea of whether ultrasound image is going to be of good quality or not. So we usually calculate this coefficient using this formula, Z2 minus Z1 square over Z2 plus Z1 square. And you remember, by Z1 and Z2 we mean the acoustic impedances of two media separated by a boundary, and this is where the incident radiation is. Part of it gets reflected into the same medium and part gets transmitted. So if this is the incident intensity, this is the transmitted intensity, and this is the reflected intensity, there is a simple equation that relates all these intensities: IR plus IT. IT is the transmitted part of the incident intensity of ultrasound radiation, and IR gives us what is reflected back into the same medium. This IR is basically alpha. So IR is the part which is reflected back into the same medium. We usually denote this by alpha. So this is the reflection coefficient. Basically, reflection coefficient, this IR is actually divided by IR. If I divide all this equation, let me divide all this equation by this incident. This is 1 is equal to IR over I plus IT over I. This is actually alpha, this one. So this is 1 is equal to alpha plus IT over I. So this part, IR over I, this is actually the reflection coefficient. That means how much is reflected divided by the original intensity. So this fraction of the reflected intensity into the same medium is known as reflection coefficient. We have several questions in the exam where these these values are given in the question. You just have to put in there, and you have to work out what is the value of alpha in this case. If you remember the last lecture, we did have discussion on questions like this. And specifically, there was a question in which we first calculated this without applying gel on the human body. This reflection coefficient had a very large value in that case. That means if radiologists making use of ultrasound, they do not apply gel on the body, all that incident radiation is reflected back into the same medium. Hardly any gets transmitted. But as soon as we apply the gel, we know it has a different value of acoustic impedance. Most of the incident ultrasound gets into the body, and a meaningful image is formed, a comprehensive amount gets into it. So that is why we have a very, very small value of alpha in that case. That was the last question we discussed. So this topic will be considered cover now. The last thing which is coming up now in this syllabus, that is about the attenuation. Attenuation is a term that is widely used when we study any kind of radiation. It could be it could become a familiar term by the end of your syllabus, because you will have learned this in the study of X-rays. You will have learned this definition or this term in the study of communication. So wherever radiation is involved, wherever signals are involved, attenuation is a natural consequence of the radiation coming and going in any medium. Attenuation is simply the gradual loss of its intensity when it is moving through a medium. So attenuation means if a signal is passing through a medium, how much of it is its intensity being lost over a time, over a distance. And there is a formula that gives us the value of how much remains of a signal when it travels a certain length of a medium. So that is the last part. We'll learn that formula and then we can start our new topic if we still have time. So let me write this attenuation at the top here. Attenuation. Attenuation is the gradual loss of strength of a signal. In this context, because we are talking about ultrasound, so ultrasound will sure have a certain strength, which means it will have a certain intensity when you make it incident on a particular part of human body. When it travels through that part of human body, that organ, its intensity will be lost gradually. So this is usually the manner in which intensity is lost. Let's say it has a certain value in the beginning, and after covering a certain length, it reduces in this manner. So with the distance, its intensity is plotted, and this is how it varies. And this type of graph means it is exponential decrease. Exponential decrease, which means gradual decrease. In simple language, exponential is gradual decrease or gradual loss in the strength, in the intensity of the signal which has entered a particular part of human body. There is a formula that gives us exactly what will be the intensity of that signal after covering a certain distance of that particular medium. Let's say this was I naught in the beginning. So original intensity is I naught. The formula which gives us the value of this intensity at any particular instant will be I naught E raised to the power minus mu times X. Let me write it big so you can see what I have written here. This is I is equal to I naught E raised to the power minus mu X. This is something new now. This mu, a Greek letter mu, this is known as attenuation coefficient, is attenuation coefficient. That simply means this is something to do with a particular medium. If its value is large for a particular medium, there will be a faster loss of energy in it. So we have the original signal going to be weak very, very quickly. It will not be able to cover much of distance if mu has a large value for a particular medium. But if for some media, mu is small, usually mu is large for bones. So denser media like bones, they have large value of mu, so naturally ultrasound will not be able to pass through them. Maybe they quickly lose their strength, but compared to some other media which don't have a large value of mu, the intensity will not be lost that quickly, so a large distance is covered. So if there are two graphs given, suppose you start with the same value, and this is what this. So this is the kind of situation which is for large value of mu. This is for smaller value. Of course, when we have small value of x, there will be a gradual loss, and it will take a very long distance before this practically becomes zero, although theoretically it's very long distance over which we have some value of it, because exponential means x needs to be very, very large to make it zero. So that means mathematically, that means it should be infinity. So it doesn't touch this graph even after very large values are involved here. So usually the graphs ends somewhere close to it if it's very small, and practically that is considered zero, but it doesn't touch that axis. So this x will be very large. That means it will be able to cover a very long distance if mu is small. So mu is the attenuation coefficient which determines how much length the incident ultrasound will travel in a given medium, And with this, we finish, because naturally there are questions in the exam in which the original intensity given. Let me means and how we handle it on a calculator. So let me quickly give you the idea of what this equation, how this equation is handled. Suppose there is a certain value of original intensity is given, and they give you this value x in centimeters. Let's say this is the thickness of a certain medium, and this is the incident radiation, and they give you the value of the intensity upon entering this medium. So you know this is I naught. So let me start it here. So if the original signal upon entering a certain medium in I naught, definitely it is going to be different here. So this will be I. If it has covered a certain length x. This is the length of that medium in which ultrasound has traveled with this value originally upon entering, and this is the value that will remain because it will gradually lose in its strength, and this is the intensity that will remain upon reaching the end of this medium. So I want to calculate the value of I over I naught. This is usually what they ask, the fraction of intensity that remains when it reaches the other side. So I over I naught is simply E minus mu x. Suppose I know this is just 4 centimeters across. 4 centimeters. The width of it is 4 centimeters. So I write 0.04 in meters here. And let's say I know the fraction that reaches here is 50%. So 0.5. Half of it remains when it reaches there. So 0.5 is an assumed value. E minus mu. Mu remains something to be found. I don't know what mu is. So let's see how we handle this type of question in which mu is unknown. I know what fraction remains when this signal reaches there. So that is 50%. That means 0.5. Half of it remains. And this is 0.04 in meters. So you have to find the value of mu. How do you do this? When you take the natural log of the two sides, this also becomes minus because this is less than 1. So when you take the natural log of it, you get minus natural log of 2. So this will be probably 0.693, a number like this is equal to, with negative sign here of course, and when you take the natural log of this, this disappears. This exponential function disappears when you take the natural log, and this side will become minus 0.04 mu. That means all of it is written here with this E missing. So E goes because you have taken the natural log of it. Now the two sides are very simple to handle because this is a simple equation. So mu is now 0.693 divided by 0.04. So this will be the value of mu, and this is how you handle this equation. Most of the questions are of this type. Sometimes the value of x is to be found. Sometimes mu and x both are known, and you just have to find what fraction of the intensity remains upon reaching the other side. And I hope you know how to handle. Let's say if you know these two values, you multiply and you go to the calculator and see there is an exponential function there. A small e is written with the x here. So this e written with x here, this is how that function looks like. And you use that button and this e appears there. You write this product here in the place of x, and then the value appears here. So when this value appears here, that means you know the fraction of that intensity which reaches the other side. That means if I is equal to I naught E minus mu x. Suppose I know both of these numbers. So I over I naught is equal to E minus, let's say this is something like 3.5 and this x is 0.04. So all that you have to do is you multiply these two numbers, you get something like suppose you 0.12, something like this. So you use the calculator, you write exponential function there, this e appears on the screen, and in that power of this you write minus 0.12, and it gives you a certain value of it, which is usually a positive number, and that will give you, suppose this number appears to be 0.53, something like this. That means 53% of the incident original intensity goes to the other side, and if it appears to be smaller than this, let's say 0.11 is the number, that means only 11% remains when it goes to the other end. So this number gives us the idea of what percentage of the incident, the original intensity, loses its energy and goes to the other side. So this number gives us the fraction of the intensity that reaches the other side. This is all about the use of ultrasound in diagnosis. The last part in oscillations, I'll share with you the worksheets related to this discussion on Tuesday. Meanwhile, you can go through all this detail, go through some of the past papers. Hopefully by tomorrow, I'll upload, and if not tomorrow, on the very next day when we have the class, before that, I'll upload this. So you have a few questions for practice. And then afterwards, on Tuesday, we'll be in a position to start our next topic, and that is electric fields. Thank you for today.